All right, analysis of covariance, ANCOVA. Analysis of covariance is a blend of ANOVA and regression. The continuous independent variables are called covariates, and the categorical independent variables are called factors. A covariate is an independent variable that can influence the outcome, the dependent variable, but isn't of direct interest. It's analogous to matching and blocking, but ANCOVA matches participants mathematically rather than by physically forming pairs or blocks of similar participants. Graphically, we have a covariate and a grouping variable, and they both share variance with the dependent variable. This is the variance explained by the grouping variable. This is the variance explained by the covariate. Once we remove the variance explained by the covariate, the ANCOVA determines how much variance in the dependent variable can be attributed to the independent variable after controlling for or removing the variance explained by the covariate. All right, if you have a study design where you're measuring the same dependent variable in two or more independent unrelated groups over 2 time points, an ANCOVA might be appropriate. For example, you might want to determine any changes in blood pressure before and after different types of exercise intervention. As you believe the post-intervention scores will depend to some degree on the pre-intervention scores, you compare differences in post-intervention scores between the interventions with the pre-intervention score as the covariate. Another way you could do this would be to use a mixed ANOVA. You could reduce the effect of an extraneous variable. So if you have a study design where you're measuring a dependent variable in 2 or more independent groups and you want to control for the effect of another variable known or thought to influence the dependent variable, an ANCOVA might be suitable. For example, say you wish to compare the differences in cholesterol concentration for different physical activity level groups, you might use a body mass as a covariate, as this will also have an impact on cholesterol levels. So here's some examples of covariates. You're comparing the salaries of men and women to see who earns more. One factor that you need to control for is that people tend to earn more the longer they are out of college. So years out of college, in this case, is a covariate. You're running an experiment to see how corn plants tolerate drought. Level of drought is the actual treatment, but it's not the only factor that affects how plants perform. Size is a known factor that affects tolerance levels, so you would run plant size as a covariate. Say you want to know whether or not there are three types of studying techniques impact exam scores, but we want to account for the grade that the student already has in the class. So we use their current grade as a covariate and conducted an ANCOVA to see if there's a statistically significant difference between the mean scores of the 3 groups. So we have some assumptions. You have one DV that's continuous. You have one categorical IV that consists of 2 or more groups. You have one continuous IV that's covariate. And you have independence of observations. The covariate is linearly related to the dependent variable at each level of the independent variable. We have homogeneity of regression slopes. We have residuals that are normally distributed. We have homoskedasticity, which is the homogeneity of variances, and we also have no outliers. So let's do an example. Dana wishes to assess whether vitamin C is effective in the treatment of colds. To evaluate her hypothesis, she decides to conduct a 2-year experimental study. She obtains 30 volunteers from undergraduate classes to participate. She randomly assigns an equal number of students to 3 groups: placebo, group 1, a low dose of vitamin C, group 2, and a high dose of vitamin C, group 3. In the first and second years of the study, students in all 3 groups are monitored to assess the number of days that they have cold symptoms. During the first year, students don't take any pills. In the second year of the study, the students take pills that contain one of the following: no active ingredient, a low dose of vitamin C, or a high dose of vitamin C. Dana's SPSS data file includes 30 cases and 3 variables: a factor distinguishing among the 3 medication groups, a covariate, which is the number of days with cold symptoms in the first year before any treatment, and a dependent variable, the number of days with cold symptoms in the second year when they are taking the pills. So the research question and hypotheses. So my research question is, do 3 different levels of vitamin C impact the number of days of cold symptoms in the second year of the study, controlling for the number of days of cold symptoms in the first year? So my null is that 3 different levels of vitamin C do not impact the number of days of cold symptoms in the second year of study, controlling for the number of days and so forth and so on. And then the alternate is the 3 different levels of vitamin C do impact the number of days. So we're going to start with assumption 5. We'll go to that the covariate should be linearly related to the dependent variable at each level of the independent variable. So we have to do something a little bit different. We go to data and we come down to split file. And then we're going to say, this one's hyperchecked, but we're going to click this one and say organize output by groups, and we'll bring the groups over. And then we click OK. So the covariate should be linearly related to the dependent variable at each level of the independent variable. Go to Chart Builder, Scatter Plot, move pre to Y, and days to X. Click OK. On each graph, you can double-click elements. Double-click it, it'll pop out. Click elements and come down to fit line at total. And then it'll give you the fit line for each, and you can see that they're each linearly related at each level of the dependent variable. So then you have to not forget, you can't forget to go and reset the split file, or everything else you do will be split out by the grouping variable. So you just go back to this recall dialog, come down to split file, and then just hit reset, and then OK. Okay. Homogeneity of regression slopes. This means that the interaction term cannot be significant. So we have to check the interaction term. So we go to Analyze, General Linear Model, Univariate, move the variables over, and then click the models. We have days as our DV, the fixed factor is group, and pre-days is our covariate. We click Model. This full factorial will be checked. We want to click Build Terms. So we click Group and move it over. We click pre-days and move it over. Then we hold down Shift and click them both, and the interaction will be done for us. Then we click Continue and then OK. So then we have to come down here. Our first table just tells us the levels of our factor. So this is what we want to see. If we have significance for the interaction term, we can't do an ANCOVA. We might have to go back and do a mixed repeated measures ANOVA. But we don't have a significant interaction here, so we have homogeneity of regression slopes because this is not significant. So there was homogeneity of regression slopes as the interaction term was not statistically significant, and I report the F statistic. Now, it's a bit counterintuitive, but in order to continue checking assumptions, you need to keep going and run the ANCOVA to get some of the saved items you will need to check assumptions. So we're going to go ahead and run the ANCOVA and then come back to those findings after we check assumptions. So we'll go back and do the ANCOVA, go back to recall recently used dialogues and pull up the univariate, and everything will be set. Click Model, and then we'll go back to the full factorial, and then click Save, and then click Standardized and Unstandardized. Then click Estimated Marginal Means, and we're going to do the same thing, compare main effects and Bonferroni. Then we'll click Options, and we're going to add the homogeneity test and click Continue, and then click OK. So assumption 7 is that our dependent variable should be approximately normally distributed for each group of the independent variable. We'll run an Explore with the ZRE1 saved variable, which is here, as the dependent variable, and group as the independent variable. So we go to Analyze, Descriptive Statistics, Explore, move variables over, and click Plots. Uncheck the stem and leaf, and click the normality, and we're going to say Continue and then OK. And we can see that we have normal distribution for all levels of the grouping variable. Standardized residuals for the interventions were normally distributed as assessed by the Shapiro-Wilks test. So now we're going to check the overall normality, which is easy. We just go to the recall dialog box and pull up Explore and then kick out the groups and just in the factor list and click OK. So we just want to look at this and say OK. And we can see that those are also normally distributed. Standardized residuals for the overall model were normally distributed as assessed by Shapiro-Wilks. Then we want to look at homoskedasticity or equal variances. We asked for the Levine's test, and we can see also that that is not significant. So we have equal variances. Finally, we need to see if there are any outliers. We can do an Analyze Descriptive Statistics descriptives of our standardized residual variables. And we see that there are no plus or minus. We're at negative 2.25 and 1.93. So we're within plus or minus 3. So we can assume no outliers. So now we scroll back up and we evaluate our output. So this between subject factors just tells us about the levels of our independent variable. This table presents the means and standard deviations and sample size for each dependent variable, for the DV for each group of the grouping variables. We have the placebo, which has the highest number of days with cold symptoms. We have the low dose of vitamin C and then the high dose of vitamin C. And these are just descriptives, unadjusted means without considering the covariate. All right, so then you see estimated marginal means. These are the adjusted means which account for the covariate. It is these means that are being compared when the independent variable is being tested for statistical significance. See how they're different than the table on the previous slide? This is after controlling. So now we actually have the placebo has longer days of cold treatments, and the low dose and the high dose have actually shorter days, except for the high dose goes up a little bit. So we say adjusted means are presented, number of days with cold symptoms in the second year was greater than the placebo group, etc., etc. Okay, so now we want to know whether there was an overall statistically significant difference in days with cold symptoms in the second year on the vitamin, which is the days variable, between the different interventions, which is the group variable, once their means had been adjusted for days with cold symptoms in the first year, which is the pre-days. So we're looking at the grouping variable, and we want to know, is that significant? And we find that it is. After adjustment for first year days with cold symptoms, there was a statistically significant difference in second year days with cold symptoms between the interventions. And you write out the F statistic. Then we can look at the pairwise comparisons, and we see that the placebo is significantly different than the low dose, and the placebo is significantly different than the high dose, and that the low dose and the high dose are not statistically significant. So we will report that out. Days of cold symptoms was statistically significantly greater in the control group compared to the low dose vitamin C group and compared to the high dose vitamin C group. There was no significant difference between the low and high dose vitamin C groups. So then we write up our final report in APA. An ANCOVA was run to determine whether there was an overall statistically significant difference in days with cold symptoms in the second year on vitamin C between the different interventions, which was the group, once their means had been adjusted for days with cold symptoms in the first year, which is the pre-days variable. After adjustment for the first year days with cold symptoms, there was a statistically significant difference in second year days with cold symptoms between the interventions. Examining Bonferroni adjusted post hoc tests show that the days of cold symptoms was statistically significantly greater in the placebo group compared to the low dose and the high dose vitamin C groups. There was no difference between the low and high vitamin C groups. The thing about ANCOVA that you need to really be careful with is whether or not you violate the homogeneity of regression slopes. Because if you do, if you violate that, you really have to stop, and you would maybe go and do mixed repeated measures ANOVA. But otherwise, if you don't violate that assumption, then ANCOVA will be fine.